Good afternoon, everyone. First of all, I would like to thank the Ascent project to invite me and propose me for giving me this webinar on algorithm photoemission that we actually implement in Grenoble in the so-called KPEEM technique for bond structure analysis, and it is a technique which is particularly suited to two-dimensional materials. So here you have in the inside a picture of the buildings where the lab is actually sitting, and behind you have a flavor of the mountains surrounding the Grenoble city. So the agenda of this webinar is as follows. I will provide you with a short introduction to photoemission with an overview and some requirements for bond structure analysis. Then I will start the core of the presentation with the principle of photoelectron emission microscopy for looking smaller, actually. So providing photoemission with lateral resolution. And then I will go through the different kind of informations available from KPEEM through selected examples before concluding. So photoemission, what is photoemission? Photoemission is the photon in, electron out technique. So you shine your sample with photons and you analyze electrons emitted by the sample by the so-called photoemission process. And it is actually a technique for probing occupied electronic states. So at the bottom left, you have a rough spectrum of a schematic spectrum of the what is emitted by the sample. So according to the speed of the electrons, the kinetic energy of the electrons, and you have different spectral features. At low kinetic energy, you have so-called secondary electrons that can escape from the sample surface at fairly low energies. At the other edge of the spectrum, you have electrons being emitted close to the Fermi level of the sample. So this is the highest occupied electronic state in a metal, for example. And in between, you have core level states. These are the electrons sitting on a particular atom in a particular core shell. So you have basically two kinds of conservation laws behind photoemission. For core level electrons, you have an energy conservation law. So the kinetic energy can be deduced from the binding energy of the electron and the excitation energy h nu. And for valence electron, you have a momentum conservation. So basically, the momentum of the electron parallel to the surface will be conserved in the crystal and in the vacuum. So experimentally speaking, you have a spectrometer which is measuring the kinetic energy distribution and the momentum distribution of the emitted photoelectrons in order to provide the requested information. So core level electrons will be providing an information related to chemistry, and valence electrons will provide information relative to electronic properties. So a very quick illustration regarding chemistry, chemical fingerprinting. So this is so-called XPS, X-ray photoelectron spectroscopy, and I've selected the very important case of graphene cleaning. So when you grow graphene on a copper foil with CVD, and you want to transfer this graphene film onto a technological surface, you need to cover the graphene by a polymer, which is usually PMMA. And this PMMA will help you to transfer the graphene film onto the final substrate. But then you need, after transfer, to remove this PMMA. And I've been displaying a series of spectrum of the carbon 1s emission, carbon 1s photoelectron. So this is a K shell of carbon. And as a function of a cleaning of PMMA using acetone. So in the first situation in spectrum number A, you have the fingerprinting, the chemical fingerprinting of PMMA, because PMMA is very thick. The photoelectron from graphene cannot escape from the PMMA, so you see only the fingerprint of PMMA with different kind of chemical bonding that you have in PMMA. And then when you start cleaning for longer time the graphene, you start see to appear the sp2 fingerprint of graphene, which is finally in the C situation very well detected, but you still have some PMMA residue. So this gives you a flavor of how powerful photoemission is when it comes to detect and to investigate chemical bonding and how clean a surface is. Coming back to bond structure analysis, you have several requirements. So I've showing you this very important momentum conservation law. So which tells you essentially that at low kinetic energy, you will have an enhanced momentum resolution. And this is the reason why in ARPES, for bond structure analysis, we usually shine our sample with fairly low energetic light using helium emission at 20 and 40 EV. Besides spectral resolution, you also need a spectral weight. So you need to care about the similar intensities of the bonds that you're measuring, and this is very much dependent to the geometry of the experiment, because actually in photoemission the transition probability is scaled with the square of the so-called matrix element, in which you find the polarization vector A and the momentum operator which is acting on the electron states. So it can well be that because the direction of the light is not ideally suited, you have extinction on certain bands, and this is illustrated here, where at the gamma band you don't have any signal, and you need to have simulation. Can you see my screen still? Sorry, I switched to the.
Yeah, we can see this. Oh.
Right. Okay. Sorry.
Yeah, you just switch them again, you'll find it.
Right. Okay.
Yeah, that's all good.
The third requirement is lateral resolution, because as all of you may know, when dealing with 2D materials, you usually have micron scale devices or micron scale domains. So microscopy is necessary, and the fourth requirement is to in order to broaden the access time to this technique, which is usually implemented with synchrotron at synchrotron radiation facilities, you need to have laboratory instruments, and this is where KPEEM enters the game. So, what are the principles of PEEM and KPEEM? So this is a picture of the instrument we are using. So basically, PEEM is only a microscope being added before the spectrometer, so before the device that will analyze in energy and in momentum the electron distribution emitted by the sample. And in this particular example, the spectrometer has a form of two hemispheres in series. And what we essentially do is that we are recording image at each energy. So this is spectroscopic imaging, meaning that the data you have at the end is a 3D data set in which you find one spectrum at each image pixel. Different kind of PEEM images. On the top right, this is a conventional secondary electron PEEM, which basically carries an information regarding the work function of your sample. In this particular example, you have two areas. The bright area is pure graphene, and the dark area is molybdenum diselenide, one monolayer covering graphene. And by selecting a particular area on the bright or dark zone, then you can reconstruct the bond structure. This is a KPEEM image. It's the second kind of image. Besides those two kinds of images, you can also record elemental images, which will be telling you about the particular chemistry of your sample at a particular region of interest within the image. So here you can find, for example, a crystal of molybdenum diselenide, about 30 microns in dimension, and deposited onto silicon, and you see clearly the molybdenum, sulfur, and carbon, silicon, and oxygen distribution. So this is a picture of the instrument we have in the lab. Just to give you a flavor of how it looks like, we are working in ultra-high vacuum, like in conventional photoretinal spectroscopy. So this is an additional constraint. We need to clean the surface before analyzing it, and we have to carefully manipulate samples when we travel the sample between different chambers. So we have different kind of PEEM instrument design existing. Here in Grenoble, we are using the NanoSK instrument from Scienta Microns. This is a picture on the right, as opposed to more conventional designs provided by Elmitech and Specs. Both instruments have its own advantage. The NanoSK is very powerful because it can provide at the same time very high energy resolution and reasonable lateral resolution. So the instrument basically has a strong peculiarity of providing both images in direct space and reciprocal space. So this is a schematic of the series of lenses that are used to create the image of the sample surface and to actually project this image in order to make an enlarged image at the end, impinging the detector. And there is an easy switch between both modes, because you basically move the object plane from the sample surface to the diffraction plane in reciprocal space, to the diffraction plane of the objective lens, which is basically where you can have access to the angular information. So in the reciprocal space, for performing band structure image, you are actually imaging the angles of the electrons, as opposed to the direct space where you image the positions. And by switching from one zone to the other, you can reconstruct a specific band structure image of the specific area with a very good control over the area selected, because you have this easy switch between both modes. So here I'm providing you a comparison between ARPES, which is really the initial technique that has been developed since the early times of photoemission for band structure analysis. So in ARPES, you're actually analyzing the reciprocal space by just rotating the sample. This provides a fairly poor localization. You don't have any kind of lateral resolution with this mode. However, you have a very good energy and momentum resolution, but it is intrinsically slow because you have to rotate at each time the sample and then acquire a spectrum. In PEEM, what you are basically doing is you are analyzing the angle, the whole set of angle at a particular energy. So it is very fast. But it provides an energy and momentum resolution which is slightly degraded compared to ARPES. Okay, then you have I'm providing you an example of the whole set of band structure image in the case of graphene on silicon carbide at the left. I will be playing again. So you see all the direct cone of graphene. So the band structure starts from the Fermi level and goes to higher binding energies. And so this is the first case on the left, and on the right you have the same case with on top a molybdenum diselenide layer covering graphene, and you find both the bond structure of molybdenum diselenide and graphene. These are raw data, so very nice images that you can use without almost any kind of post-treatment. Informations from KPEEM through selected examples. So we start by molybdenum disulfide grown by CVD on silicon surfaces. This is a collaboration we had with Rutgers University some years ago. And actually Mathieu Fregnault, the postdoc in charge of this topic, was working on this kind of sample. So this is a movie where you have the bond structure of the molybdenum disulfide, single layer molybdenum disulfide appearing. Okay, now you see the screen. And out of this stack of images, of momentum images at each energy across the valence band, you can make a cut along asymmetry directions in order to get the desired bond structure. What you do with this bond structure is first that you, for a monolayer molybdenum disulfide, the valence band maximum is located at K, as opposed to the situation for the bulk, where you have the maximum located at gamma. And this is actually what you can see here on this bond structure. The energy separation is small but significant, with the valence band maximum being located at K. And this is a fingerprint of the monolayer molybdenum disulfide. Out of this bond structure, you can make a curvature analysis of the upper valence band, and this will give you access to the effective mass of the holes along a particular direction, so either at gamma or at K. So we did that for this particular case, and actually we find this figure, and we can compare this figure with other data from literature. So I recall here that we are analyzing CVD grown molybdenum disulfide domains. The effective mass is 2.0, the free electron mass. And this is quite similar to a case where we have exfoliated molybdenum disulfide supported by a substrate. And you see that in the case of exfoliated domain suspended in a kind of grid, and this is the reference I'm showing here, you have transport properties which are very different, very much different, because the effective mass is actually very sensitive to the substrate, and this is what we wanted to show. So, analyzing the effective mass in a very easy way will tell you about the transport properties of your 2D material and how these transport properties can be possibly modified by a substrate. Besides this effective mass, you can derive the surface in plane lattice constant just by measuring the momentum separation at the K point and the gamma point. This momentum separation will be somehow related by a more or less direct relationship to the in-plane lattice constant. In this particular case of molybdenum disulfide, we find an in-plane lattice constant, which is 3.55 angstrom, which is very significantly larger than the bulk case, which means that our film is somehow in expansion as deposited on the onto the silicon substrate. So you have an intrinsic strain of your stress of your molybdenum disulfide domain as deposited on the substrate. We've also been performing this stress state analysis in the case of molybdenum disulfide grown on sapphire using van der Waals epitaxy. So it's a different kind of deposition technique. And we wanted to compare this situation with the previous situation where we had CVD growth. So we do the same. This is the series of KPEEM images, the reconstructed bond structure along the gamma KM direction. And in the dashed lines, you have the simulation of the bond structure in the case of an unstrained molybdenum disulfide. And you see that actually both are matching very nicely. And if you measure against the gamma K distance, you find, when you measure the in-plane lattice parameter, you find the in-plane lattice parameter very, very close to the bulk situation, which means that in this particular case of van der Waals epitaxy, you have a molybdenum disulfide domains that are almost completely decoupled from the substrate, which is actually expected by this deposition technique. So you have a very easy way and very precise way to address the stress state of your 2D material film. What about heterostructures now? So the first case I am presenting here concerns molybdenum diselenide, one layer molybdenum diselenide deposited onto graphene on silicon carbide using van der Waals epitaxy. I've been showing you some previously some bond structure images, KPEEM data, the movie, with the two different kind of bond structures. On the picture on the right, you see very nicely the three sets of direct cone of graphene, and so the K point of the bond structure of graphene, and next to them you have the three sets of K point of molybdenum diselenide. And you actually see that those are aligned in plane, which means that you have you have a good orientation of both lattice, of both crystalline lattice between molybdenum diselenide and graphene, with almost no in-plane rotation. And this analysis is possible very easily because you have an equal spectral weight of the bond structure between graphene and molybdenum diselenide due to the particular geometry of the instrument. On another kind of sample, you see that you have a bond structure which is very much different, with different sets of K point, which means that you have two crystal orientation for the graphene substrate, and therefore also two two orientations for the molybdenum diselenide. Okay, so this is again a bond structure derived from asymmetry cut of the KPEEM data, where you find again the valence band maximum being at the K point, which is a fingerprint of monolayer molybdenum diselenide, and again you can derive the effective carrier masses. Right. So now I'm again going into increasing complexity of the samples, dealing with heterostructures between molybdenum disulfide and tungsten diselenide, itself being deposited on silicon. This is CVD grown. This is a collaboration with EPFL in Switzerland, Professor Andraskis. And this is for investigating the physical properties of such device in terms of photo detection. So the PEEM image displays actually different kind of domains. You have onto the silicon substrate, which appears in light gray. You have patches, stains, which are the fingerprint of single layer molybdenum diselenide directly deposited onto silicon, but you also have molybdenum disulfide being deposited onto the large tungsten diselenide crystal, and these are these heterostructures that we will be interested in. So you can, as I was saying previously, the KPEEM instrument has its strength in the ability to select a particular area of interest and to record very reliably bond structure data for this particular area of interest without having shifts during this process, switching from direct space to reciprocal space. So we can very reliably select different areas on the image and record the bond structure. So you have the fingerprint of the bond structure of a single layer molybdenum disulfide, single layer molybdenum diselenide, but also the heterostructure with molybdenum disulfide and tungsten diselenide, which is actually a mixture between the bond structure of molybdenum disulfide and tungsten diselenide. And when you are looking more closely at this data, you can, because you have these three data sets, so the momentum images at each binding energy below the Fermi level, you can isolate the contribution. Carefully looking at the series, image series, we can isolate the contribution of the tungsten diselenide and the molybdenum disulfide and see how they rotate, they are rotated. And like this, you can more or less easily determine the twist angle between both atomically thin layers. So I'm going to finish by a practical application, actually, in the field of 2D materials. And I'm coming back to the issue of graphene cleaning that I introduced you at the very beginning of this talk when I was mentioning the chemical fingerprinting of photoemission. So you know that we are looking at a way to efficiently clean the PMMA after transfer of graphene onto a technological substrate. And actually, this PMMA is quite complex. You have bulk PMMA, so this is a sketch on the right-hand side of the slide. You have bulk PMMA in green, and you have then self-organized, so to speak, PMMA molecule. And at the interface with graphene, you even have 2D, two-dimensional PMMA, which we call PMMA-G, which we found very difficult to remove using traditional chemical solutions. And we found that we only plasma cleaning, so dry physical process, were able to effectively remove this two-dimensional PMMA as a graphene surface. So we are successful in kind of optimizing a recipe, a plasma recipe for efficiently removing the PMMA-G, but we wanted to be sure that this plasma treatment, even if it happened at very low energy, at very low ion energy, had not been damaging the electronic properties of graphene. So we've performed the KPEEM analysis of the plasma cleaned transfer graphene surface. So this is the PEEM image. Image A is a PEEM image of this situation. We've been selecting the area for recording the bond structure, and you find close to the Fermi level a set of direct cone. And the direct cone is really the fingerprint of graphene in its almost untouched physical properties. You have a set of graphene cone just because you have an in-plane orientation of the graphene. You have different domain within the area of interest with different in-plane orientation, but you have the graphene cone, and the presence of the graphene cone in the bond structure really tells you that the plasma cleaning did not influence very strongly the graphene transport properties. So in summary, I just want to stress on the performances of KPEEM. So you can look at an area of interest larger than 5 microns, typically. It depends, of course, on the signal intensity you have. You have a very strong signal intensity for graphene, much less signal intensity in the case of molybdenum disulfide, for example. Energy resolution can be as small as 50 millivolts, millielectron volts, which is largely enough, more than enough when you study 3D materials, heterostructures. Momentum resolution are in the order of 0.05 reciprocal angstrom. So KPEEM is suitable for epitaxial films, multi-domains 2D layers with in-plane orientation, heterostructures. You have to care about strongly insulating substrates, and really it's very suitable for, I've told you about how quick the process is. So typically acquiring data takes less than 20 minutes compared to several hours for ARPES. So PhotoEmission electron microscopy using KPEEM with a laboratory source is really very well suited for systematic bond structure studies of 2D materials. I mean, keeping in mind that you need very often to screen different processing conditions, for example. And with this technique, you can really have access to such kind of diagnostic. Well, this is my last slide. I thank you very much for your attention, and I'm open for questions.
Thanks very much, Olivier. I think that was quite interesting. If you want to ask any questions, just turn on your microphone and go ahead, please.
Yes, I'd like to ask a question. I don't know, you hear me? Or?
Yeah, we can hear you. Yes.
Okay, so in conventional ARPES, and when you deal with three-dimensional materials, most of the broadening that you get for, well, energy broadening is ascribed to the dispersion along KZ. So it's KZ broadening.
Yes.
Here you have a 2D material, so you get rid of that.
Yes.
Yet you have a very large dispersion. So I guess it's a lifetime effect. And can you deduce anything from the dispersion in energy of the signal you measure? Or could you comment about that?
Well, of course, when KZ is suppressed in 2D material case, the lifetime remains, but also the broadening coming from the spectrometer itself, which is.
But you are talking about a resolution of a few millieV, 50 millieV. And it seems to me that.
You mean the dispersion in energy?
Well, what is the origin of the dispersion in energy of the spectra you showed?
But this is the spectrometer itself.
Okay.
So the spectrometer itself, the energy analyzer, the hemispherical analyzer has a fixed, broadening, which is quite large compared to other physical effects. For example, thermal broadening or lifetime broadening. So this is the main contribution to the energy broadening.
Okay, yeah. Thank you.
Yeah.
Thanks, Thierry. Any other questions? Listen, you all have, when you register for the webinar, you have my email address, so you can think of anything else, just give me a shout and I'll pass the questions to Olivier. And as I mentioned before, the webinar has been recorded, so if you missed the beginning or you have a colleague that could be interested on, it will be up in the website in a couple of days, so you'll be able to watch it again. So I think I want to finish. So if there's no other questions, thanking Olivier again. I think it was quite interesting. I hope it was interesting for you too. And this is the last of the Ascent Plus webinars this side of the summer. I know people go on holidays and so on, if you can. So we'll have no webinars now in the next couple of months, and we'll hope to start again with webinars in September, October. Thanks again for attending, and if you're going on holidays, have a nice break, and see you in the autumn. Take care.
Goodbye.
Bye-bye.